In this video, we're going to take a look at coroutines. I always wonder whether or not I should show coroutines in the beginning course, but I've decided that you really need to learn how to do this, and it's the sort of thing that really you can't make an advanced game without using coroutines. So here we go. Coroutines are a programming technique. They're not necessarily something that's built into Unity, although they are built into Unity. They are not Unity specific, though Unity does give us some coroutine specific language that we can use to make coroutines and create them fairly easily. So what is a coroutine? We've talked about this in the lectures. The coroutines are basically code that can run over the span of several frames, and that's a very Unity specific definition. And since this is a Unity course, I'm just going to leave it at that. But if you want to learn more about coroutines from the perspective of a broader perspective of general programming, then you can certainly do some research online and find out how other languages use coroutine. We're going to focus on how Unity uses coroutines. All right, so I'm creating a new project called, unimaginatively enough, Coroutines. So let me go ahead and create this. And this technique, the technique that I'm going to show you, is going to be useful for one of your assignments. You have an assignment out there for creating a die roller, and you need to know how to use coroutines in order to complete that assignment. So why don't we start by making something that is hauntingly similar? I will create a flat surface from a cube. And our final objective is going to be to have a bunch of things moving around on the screen, and we need to figure out when they've stopped moving. And this is a good coroutine problem. As I mentioned, coroutine problems, anytime you have something that's going to take longer than 1/60th of a second, then a coroutine is a good option. All right, so we've got our flat surface. We're going to need some walls because in my experience as we start moving things around on the screen, and I'm going to use physics for this, so it's going to be somewhat random motion, we don't want things to go off of the screen. So why don't we make that adjustment, and I'll just reuse my square here, or my cube I should say, and I'll duplicate it. And I'll rotate it. And I'm going to turn perspective off because it's really hard to figure things out in perspective mode. So why don't we just do that? So I'll move this down here. And I'm going to go ahead and turn the mesh filter off, or the mesh renderer off, I should say. So now we just have a collider. Duplicate it. Bring it over here. Duplicate it again. I'll bring it to the middle. Rotate it. And I'm not going to try to make it line up exactly. I just want some quick and easy barriers in there so that the objects that we're dealing with don't go off the screen. Let me look from the side and make sure that's going to be plenty high enough. That's fine. All right, so that's good. And from the side view, I'll go ahead and place the next object, which is going to be a sphere. And I'll go ahead and raise it up in the air a certain distance. And what I'm going to want to do is kind of make this a little bit of a bouncy ball. Not too bouncy or it'll take forever to stop bouncing, but that's kind of the point. So what we'll do is we'll add a physics material. And I'm clicking in the wrong place. I should be clicking over here in Assets. Create physics material. And I'll just call this bouncy. We've done this exercise before, or something close to it. And I'm going to leave this in place. This is probably okay. I'm just going to change the bounciness to around, say around 0.6. Pardon me. All right, so there's our material. Let's select our sphere again, our ball, and let's add our physics material to it. And let's take a look at it and see how it bounces. Oh, I forgot, didn't I? I need to add a rigid body component so that it will react to gravity. There we go. Okay, so that's about right. I don't want it to be too bouncy, because if it's too bouncy, it'll take a long time before it finally stops moving. And my plan really is to make several of these. So why don't I look at it from a slightly different perspective. So I'll just grab this sphere and I'll duplicate it a few times. And I'm going to put them at different heights. And we'll see if we can't fix it so that they maybe collide a little bit and bounce off of each other, just to make it interesting. Okay, so that's probably enough. I'm suddenly reminded of Captain Kangaroo. If you don't know what that is, go look up Captain Kangaroo and ping pong balls. All right, I'm going to save my scene. I'm just going to call this main. And let's see what we've got. Okay, so that's not bad. They didn't really bounce off of each other or anything fun like that. Maybe we'll have one in here that mixes it up. Hopefully that will do it. There we go. Okay, so that makes our problem a lot harder, because now these two are still moving around, and now so are these. So this demonstration is actually going to take a little while to finish, and that's really the point of this exercise. It's going to take longer than 1/60th of a second for these things to stop moving around. So this makes it a good coroutine problem. So let's go ahead and create our coroutine. I'm going to do this on what is ostensibly a game controller. So a game controller, we've made these before. These are objects that they're empty game objects, and they're usually above everything else or up out of the way. And you make them by creating an empty game object like so. I'm almost out of room down here, but here it is, empty game object. And I'll call this new game object game controller. And I'll just go through the whole exercise. I'll tag it game controller. And I'll create a script for it called anyone? Anyone? You in the back? That's right, game controller. All right, so let's go ahead and launch game controller, our script. All right, when you're making a coroutine, there's a few things that you have to do. And the first is to make the coroutine function. So let me make a coroutine function. A coroutine function, there are a few rules. It has to have a return type of IEnumerator. Make sure you don't pick IEnumerable. We just did a lab on collections, and IEnumerable would be a collection. We want IEnumerator. And now we just name it. So I'm going to call this check all objects stopped. Okay, and it's going to return, or it's going to say that there's something wrong because I haven't returned anything yet that conforms to that interface IEnumerator. So until I do that, it's going to have that red underline there, which is fine. All right, so here's what I need to do. I need to find all of the rigid bodies that are currently active. and then see if any of them are still moving. And if they're not, then the coroutine is over. All right, so that's what we're going to make. So let's get started. The first thing we need to do is get a list of all of the rigid bodies in the scene. And we do that, as we mentioned recently in one of our collections labs, using the find objects method, which is built into the game object static class. So I'll say var all game objects. Actually, why don't we call it all rigid bodies? So we remember what we're working with. We'll say all rigid bodies equals find objects of type. And for our type, we're going to use rigid body. There we go. And remember our angle brackets, those are generics. Anytime you're working with a generic, you're looking to put a type in there. So any type will work. Okay, next I need to see if anything is still moving. For this, I'm going to actually make a private instance variable up here at the top. So I will do this. I'll say private bool. I'll call it all stopped. And I'll just initialize it so that it's false. So that's a good starting point because I know as soon as the game starts that those spheres are going to drop and they're going to instantly start moving. So it's, I think, a safe assumption to assume that when at the instant that the game starts, something's going to be moving. All right, so let me come back down to my coroutine code. And let's add a little bit more. Now this might seem a little counterintuitive, but bear with me because I think it'll make sense to you at the end. This is typically how I do any sort of if statement or any sort of loop where I'm looking for a condition to be true. I go ahead and set it to true. And then I basically go about trying to disprove that. Sorry, true is lowercase t in C#. I'm afraid I've been working with Python code this morning, and in Python it's a capital T, and that confuses Visual Studio. Okay, so we're setting that to true, and now we're going to go about setting that back to false if we can. So I'm going to use a loop and pause for a minute and think about what kind of loop I'm going to use. In our collections lab or in our loops lab, they were the same lab, come to think of it, we wanted to look at the different kinds of loops and how they're used and what the best candidate is. So what are we looking at here? This is find objects of type. And if we go look at this, we can see that it is, based on the documentation, an array. So it says rigid body, and you see those square braces there. Anytime you see a square brace, you know you're talking about an array. A collection at least, but in this case, definitely an array. All right, so which ones do we use? Which loops do we use with arrays? And the answer is for next loops. So let's make this a for next loop. So let's say for var I equals 0, I less than, and now we need the upper boundary. It's not a fixed number because we may add more spheres later on, so why don't we be flexible? I could go over there and count them, or I could just say all rigid bodies dot length, and that would give me however many are in that list. And that's great because if I add or remove spheres from my scene, then I'm still good. I don't have to come in here and change my code. Changing code, you should only change code if you absolutely have to, especially once you get it tested and working. All right, and then we just put our incrementer in there, and now we're ready to go. So there's our for loop, and now we're just going to go through and check every one of these game objects. So to do that, I'll use an if statement. So I'll say if, and now I need a reference to the current game object from the list. I'll say all game objects, all rigid bodies. The current one, which is I, we'll dereference it using I, dot, And let's see if we can find anything in here that will tell us whether or not it's still moving. This is usually going to be a Boolean, and if you want to find Booleans in a given class structure, the best thing to do is to type is, because most of the time people name Boolean properties as is, with is at the beginning. This is actually a Java convention. In Java, they really hammer this, but in C#, it's just sort of a good idea. All right, so here we have is sleeping. And so that's what we want. So this is going to tell us whether or not the rigid body is sleeping, which is the same thing as is it moving or is it not moving. If it's sleeping, then it's not moving. Now this might seem like an attractive proposition, but what we really want to know is whether or not it's not sleeping, because I mentioned earlier, we're trying to prove that that's false. So why don't we say if it's not sleeping? Just add an exclamation point to the beginning of this. That turns it into opposite day. That says if it's not sleeping. So if all rigid bodies, I spelled this wrong, didn't I? Oh no, I didn't. They're all like that. Let me refactor this, because that will bug me. I'll right click, select refactor. I'm going to have more stuff in my menu than you will because I've got third-party tools installed. But this refactor is available in Visual Studio stock. So I'll click rename and I'll say all, almost did it twice, rigid bodies. There. Okay, and that changes it everywhere. All right, so again, our objective is to prove this to be false. And so we added our exclamation point here. We're looking for the false condition. And if we find one, then we're going to say all stopped equals false. And then we're going to, let's go ahead and shoot out a debug message so that we know which one is still moving around. So it's debug.log. We'll get, again, the current rigid body from our loop, and we'll get its name. And then we'll just add to that is still moving. All right. Here's another hallmark of coroutines. And that would be the yield statement. Let me move down a little bit so we can see a little bit more. So we're going to say yield return null. Okay, so yield return null. The yield statement is specific to coroutines. So yield, basically what this is saying is, as you're running this function, this method, and we hit that 1/60th of a second, that frame marker, the frame is over now where this was executing. This basically says, hey, let's put a bookmark in this, and when the next frame comes around, we're going to pick up processing wherever we left off. Another way to look at it is, this is going to take longer than 60 seconds. The yield statement is going to say, okay, everything else in the game, why don't you go ahead and run your frame, and then when it comes back, then we're just going to keep going once you've done all that. So it's kind of two ways of looking at it, but they really mean the same thing. Everything else is going to keep going and then come back, and it really is sort of like pressing pause while everything else completes, and then unpausing and picking up your code where it left off. Okay, so that's what yield does, and then we're not interested in returning anything, so return null is okay. And the next thing I'm going to do is I'm going to type break in here. And this goes back to a little joke that I told you in class when we were going through and learning about conditionals, and that was if your keys are lost, if you've lost your keys or your phone or whatever it is you lose in the morning, and you know it could be in one of 6 places, if you find it in the 3rd place, you stop looking for it, right? It would be silly to go ahead and check the other 3 places because you already found what you were looking for, and so that would be a complete waste of time. The break statement in C# executes that same sentiment. So in this case, we're just looking for the first rigid body that we can find that's still moving, i.e. not sleeping. And as soon as we find one, we know we can set all stopped on line 24 to false. And at that stage, there's no point in continuing going through the loop to look for something that's moving. It only makes sense to keep looking if we can't find anything that's moving. So why don't we save ourselves some cycles and go ahead and break. So break says exit that for loop, and it just goes back and just keeps looking. So that brings us to our next problem. This is really only going to run one time, right? It's going to find this, and then it's going to say, okay, I found something that wasn't moving. It's going to exit the for loop, and that's going to be the end of it. That's not really what we want. So why don't we wrap this in one more loop? That way we can see two of the loops that we've studied recently in our loops lecture. And let's add a while loop. So let's put it right below where we create the list. So for our while loop, I'm going to say while. Actually, we need it below all stopped, don't we? Because that's going to be our condition. Let's put it here. While all stopped equals false. Okay, so as long as it's false, it's going to continue to execute that for loop. So this is what we really want. So let's get rid of this end closing brace. We'll go down to the bottom. We'll add it here. Hopefully that will reformat everything and make it look nice. And now I think we have a pretty good shot at finding whether or not everything has stopped moving. And then outside of our while loop, why don't we just throw a little debug statement in here that says that we have managed to satisfy our condition. So I'll say debug.log. We'll say all is calm, and now I feel like Christmas. There we go. All right, so I'll save this. Looks pretty good. Don't see any obvious mistakes. There's no red squiggly lines. You'll note that this is good to go. Now we can't run it yet because there's one more step we have to do. I can see in my copy of Visual Studio that this is gray. If I click off it, you can see that this is gray. It should be white like this one. This is telling me that it's never been called. And if I hover over it, it'll tell me that. It'll say it's never used. So I've got this great coroutine, but I'm not using it. So I need to add some code that actually starts my coroutine. This is a Unity specific command, and it is unimaginatively named start coroutine. The only thing that's confusing to beginning programming students about start coroutine is that it takes a function as its argument. We had a brief discussion on what lambda languages are, C# being a lambda language. Lambda languages allow you to pass functions as arguments. And so this is what we're going to do here. It's not passing the name of the function as a string. It's actually passing the function as a reference. And so what we'll do is we will pass this in by saying check all objects stopped with parentheses like so. All right, so that's going to pass that function in. Eventually it will return, and that will satisfy start coroutine. All right, so we're all set. Now we can try this out. And I'm going to switch to I'm going to put my console up so I can see when it stops running. So let's run it. And on my console, I can see that it immediately goes to all is calm. So I've made a mistake. Let's go see if I can find it. Actually, pretty sure I know where it is. I should have gone with my first instinct on this while loop. Yeah, this should be within the while loop. So let me just take that out and move it right there. Okay. So it was going and setting it instantaneously. And now we have what we're after. Now this is going to take a little while to complete because I insisted on making them interact with each other. And you can see that it's giving you a number. I didn't go into the hierarchy down here and give them individual names, but you could have. So this is going to continue to run until everything stops moving. So I'll pause while that happens. Okay, a little bit of time has passed. I'm going to warn you at this point that you have to be patient because we've got things that are going to move around for a while. Let me switch back over to my scene view. We'll look at it from above. It looks like 4 is still moving, so let me click on 4. And I can see that it is in fact still moving around. So if that's really the only one that just continues to move around, if I'm really impatient, I can turn that one off. And now 2 is my problem. And it's just moving by a very tiny amount. That one looks fairly still. That one's still rolling around a little bit. So it takes this very, very literally. This is it sleeping. It really looks for even the minutest motion. And so now we've got this tiny motion in here that's sort of confounding our result. And I think a big part of this is the fact that we didn't really give our sphere very much mass. In fact, we didn't give it any mass at all. It's got a mass of 1, which is not very much mass. We should probably experiment with making this mass higher. And certainly when you do your die roller, you would want to do that. The die roller, though, has the unique advantage of the requirement being there only has to be 1 die. And so they're not going to be bouncing off of each other, and they're not going to be interacting, which is really what caused all of this minute motion to happen. It's because they bounced into each other. Otherwise, they would have just dropped to the floor and then rolled around just a little bit, and then they would be done. And here we have it. I have tap danced long enough that that one finally finished moving around. Let's see if 4 is still... 4 seems to be happy as well, although it's turned off, so it wasn't part of the equation. So it did eventually find it, but as usual in Unity, a little bit goes a long way. So we made this bouncy material, and we just set the bounciness to 0.6, and we didn't do very much. We didn't do anything special with friction. This probably would have gone faster if we had set our mass to be a little bit higher. So in your die roller game, as I was saying, give your die some mass. It'll be a square too, so that will help. Squares don't typically roll around very much, and so this it won't take 15 minutes for the computation to finish. But it's good for you to see that and understand that it really looks for just the tiniest motion when it's computing these things. And that's a quick and useful look at coroutines. I want to show you a few other places that are useful for coroutines. When you did your space shooter tutorial, you used a coroutine there as well. So I recommend you go back and look at that now that you kind of hopefully have a different perspective on this now that you understand it a little bit better. Find the part where they're spawning the waves of the enemies, and you can watch that video on your own. But if you go and look at it, you can see that it is in fact coroutine. So they say start coroutine, spawn waves. There's your IEnumerator. So anytime you see IEnumerator, you know it's a coroutine. And what this is doing is this is just waiting for a particular number of seconds to go by before it throws more enemies at you. And the objective in this game was to make it not quite so predictable and linear. So you're not expecting, you may be expecting your enemies to show up every 5 seconds, but they don't. They show up sometimes 5 seconds, sometimes 3 seconds, sometimes 7 seconds. There's variability in it, and that makes the game seem a little bit more believable. So there's a good use of coroutines. If you need to look up coroutines, there are a few other things in here that I can think of. There's an example, another example video. So here's one just on coroutines, and all I'm doing is I'm Googling Unity 3D and coroutines and clicking the links. So there's a good example of a coroutine. And then there's the documentation. The documentation is not all that useful because it's very theoretical. And so basically it shows you what a coroutine might look like. In this case, it's changing the color from one color to another color, but you don't see the surrounding code where you're actually changing the color, setting the color, or setting any of that up. So it sort of gives you this theoretical fade function and what it would look like if you were in the update mode, and then what it would look like if you were in a coroutine. So that's useful as well. So really what you find is that as you get proficient with coroutines, you don't use on update or your update method nearly as much. It's probably more appropriate for most things to happen in a coroutine than it is for it to happen in the update event handler. So update is great as long as you're doing something fast and simple like changing the property on a couple of objects. But if you're trying to do a lot of work in the update, or really any of these event handlers that are designed to fire once per frame, then you run the risk of overloading the computation and the game, and you're going to slow everything down with your computations. And that's where coroutines come in. So really, I mentioned at the top of the lab that you really can't do very much without coroutines, and you really can't. It's really, really important topic and something that you need to learn to master.